Alright, Jogamers. The font is here to help me. Only reason because this video is about approximations with partial derivative tangent planes, and that's pretty unreal, you can just say. So, in 3D, you don't have a tangent line. Say you had a hill. In 2D, this is your tangent line. And it's a pretty good approximation for points at near the point of your tangent line. See, it's just this much error and difference, but as we go farther and farther, the the error increases. So same logic with a 3D thing. Let's find some 3D stuff. Okay, see what it makes. Alright. So say I wanted right here I want a tangent line right here. Well, it's more like a tangent plane per se. Let me just read what it says. Tangent plane tangent to SNP defined at contain Z tangent lines at S tangent to GY and C2 contains all tangent lines. So I think what this is trying to say is we're cooked. So there is a tangent plane. Not that. Let's try to make a very small tangent plane. How do I? Let's look over it. So say this is the tangent line. Now, I don't know how to rotate my camera, but suppose that's the tangent plane, I guess. 3D view. There you go. Well, it doesn't look like a plane now, does it? But whatever. I don't even care. So, is there a way to extend this? Oh, there. It's tangent to something, suppose. Whatever it's tangent to, I guess. It's tangent some point, who cares at this point? So this tangent plane has see. So this tangent plane has values, contains all tangent lines to that one point. So what I mean by this is, say, at this point right here, there are multiple tangent lines. Say there's one right here, there's one right here, and one right here, and a million, trillion, zillion tangent lines to it. And the tangent plane contains all of So the tangent plane at P closely approximates S, the surface at P point, and obviously I've taught you in previous videos that the equation for a plane is ax plus bx plus cz, ax plus by plus cz equals plus d equals 0, where um where A is, I have no clue. Well, it's probably just the vector. That's the freaking, it's the normal vector or whatever. Anyways, in normal terms, it's z minus zo, which is the point. Say this is point. This point is po of x0, y0, c0, and this equals 2ax minus xo plus by minus yo. That's it. Oh my god. Alright. Let me just read through this. The intersection of the plane y equals yo is the tangent line t1. Okay, so basically, when y equals yo and it turns 0, and a is the slope of the tangent line, well, like, of the actual tangent, not the tangent slope, or plane, whatever. I think that's kind of obvious, whatever. And likewise, x equals xo, then it's just a line, is the tangent line, where b is the slope of that line. And it's also the slope, the slope, why it's important is because a equals fx, which I've showed you in previous videos. That's the partial derivative. So partial derivative at xo, yo, b equals fy xo, yo. So putting that together, you get what a crazy equation we're gonna get. Z minus zo equals fx. I'm not writing xo. X times. Oh my god, it's gonna be bad. It's actually gonna be bad. Only there's an easier way to write this out. Whatever. Alright, that's the equation of the tangent line plane, tangent plane line, whatever. And I said there's multiple tangent lines, right? This is gonna be a discussion for a different video, but fx and fy are tangent lines at this point and are not the same as some other ones. So like say this is f of x and this is fy, the derivative. These are the two lines that create this tangent plane, but it's not to say that there aren't any other lines at this tangent lines at this point that are kind of important, I guess, but mostly fx and fy are pretty important tangent lines to know. Right. So with that, let's get with the linear approximation of Cranky Dinky Doo. Alright, so say the tangent line is represented by a function L of xy, and it's equal to ax plus by plus d, and I hope we know what d is by now. Anyways, So we're gonna show you linear approximation and thereby f of xy is approximately lxy. I'm not writing the whole equation, right? And I'm not writing all that again. Please don't make me write that. So f of xy is approximately making me angry. X minus a plus f of y a b y minus b plus f a b, which is also the ZO, by the way. That's the ZO. And that's what it's equal to this. These two equations are equal, by the way. And this is true near AB. And the reason why I don't just write f of AB is because that would just be equal. But whatever. I mean, I don't even know why. Oh, no. It's because if I put AB, then it would literally just be f of AB. So like, yeah. That's why it's only near AB. Near AB. Alright. So, that's how I got. This is gonna be bad. So these are approximations. And here comes the increment of y. Changing y called the increment of y. Oh no. So, should I say this? The increment of y for one variable is f prime a change in x plus epsilon change in x, where the limit of epsilon approaches 0, so does, wait, when epsilon approaches 0, so will change in x approach 0. Epsilon is the difference. It's the difference between. Let me find this. I wrote this somewhere down here. I don't know what it is, but it's the difference between change in y, change in x, and derivative f prime. So this is actually where you get the chain rule. Well, I'm not gonna show it right now, today, right now, whatever. But for the multi-variable version of that, the increment of z is equal to fx ab change in x plus fy ab change in y plus epsilon 1 change in x plus epsilon 2 change in y. Where epsilon 1 and epsilon 2 are functions of change in x and change in y respectively, such that as they both go to 0, so will change in x and change in y to go to 0. Oh, it's just so annoying. If parallel derivatives fx exist near AB and are continuous, then f is different. So the differentiable dz is, this is so annoying. is equal to the partial derivative of z, which is f, by the way. Partial x dx plus partial z of partial y dy. Now, how is this important? Probably won't even get to the thing by now. This is gonna be so fun. Alright, so dz dx. Well, ain't dx just a change in variables. Dx is gonna be x minus a, and dz dx is fx of fab, and it basically looks like the form of this. I don't know why it's important, but it just is. It's in the form of this, but it's like more tougher or something. I don't know. Yeah. Yep. Yeah. Okay. So this applies for 3 variables too. Let's do some problems with it, because it's a lot of writing, not a lot of I don't even know what it does, to be honest. But let's put it into practice. Bottom most videos I made, by the way. Alright, so okay, so basically let's start with a problem like this. So we have a cone that looks like this. That's bad. We have a cone and its base is its base radius is 10 centimeters and the height is 25 centimeters. And it's a right circular cone.
But most of all, you'll remember the
And we're gonna try to find the error of epsilon. This is the error. So find the volume, the error of volume. So the volume of this is pi over 3r squared h. And the differentiable, or whatever it's called, I don't even know anymore, dv is equal to partial v, wait, was it? Yeah, partial v, partial r, dr plus partial v, partial h, dh. And that's equal to, if we take the partial of this, this is 2 pi r over 3 h over 3, and then dr plus pi over 3 r squared dh. And we gotta remember that the change in the radius is less than or equal to the error epsilon, and so does change in h from that freaking equation called the differentiable or step. I don't even know what it's called anymore. So if we take the largest error, we're trying to find the largest error, And so we should also write that dr equals epsilon. This is the largest error change in R can have. So that means dr has to be equal to that. Or something like that. I don't even know. So the increment of the change in V is approximately dB, which if we plug in the numbers for R and H, we get 500 pi over 3 epsilon because of dr plus 100 pi over 3 epsilon, which equals 200 pi epsilon. So the max error is 200 pi epsilon cm cubed. Wow, that made sense. Now, why do these dr? I have no clue. So, cage in R is less than or equal to epsilon. Less than. Less than. So the greatest value I have is epsilon, where epsilon is a small number. The reason why dr and dh are the maximum is I have no clue. Hold on. Alright guys, I got the reason why dr and change in r are the same. So remember in a function, a 2D function like this, if I want to get a derivative of this point, change in x, say approximate from here to here, this is change in x, this is change in y, then this would be dx dy. Notice that the closer we get to this point, the closer we get to the point from here to here, and then here to here, that change in x and dx are always gonna be equal. Hold on. Like, hold on, let me just draw this better. So, the line, I should color, make it a different color. So, the line, so the line right here, dx is this very small line, and let's say our approximation was, I'm putting green, was right here, and we had an approximation right here. No, I meant, God, it's very tedious. So, the approximation of the graph right here is dx, this is dy, and that's the ratio, dy dx slope, remember that? And then, if we actually got the point right here where we're approximating, this would be change in y, but then the line would still be change in x. So dx equals change in x, but dy is not equal to change in y. Now if we extend that to 3D, we can say that when the curve in 3D, the free variables x and y are their own independent variables that give whatever values they want, but the only variable that is dependent is z, just like how x is free and y is dependent on x. And so by that logic, dx is equal to change in x and dy equals change in y, but change in z is not equal to dz, but only approximately near a certain point. They're only approximately equal to each other when they're close to each other. And obviously they're equal to each other when the limit of it is turned to 0, when the distance is 0. So that is why the error for these, the highest bound error, epsilon gets to be equal to this. Yeah, that's all. They're called differentiables. This is called a differentiable, by the way.